Hello everyone, I am Dr. Gitumoni Sharma, Associate Professor, Department of Mathematics, USTM. I am going to take a class on special theory of relativity. Today's my topic is land contraction, one of the consequences of Lorentz transformation. Let me talk first about the keywords of my lecture. Lorentz transformation, consequences of Lorentz transformation, and one of the consequences Lorentz transformation. Land contraction is the phenomenon that a moving object length is measured to be shorter than its proper length, which is the length as measured in the object own rest frame. It is also known as Lorentz contraction or Lorentz Fitzgerald contraction. So, all of you know that Lorentz transformation we already discussed in our previous classes. Lorentz transformation is the relation between two coordinate system, a rest frame and moving frame with a constant velocity. And then we consider a particle which has coordinate x, y, z, t with respect to s frame and x dash, y dash, z dash, t dash with respect to s dash frame. So, Lorentz contraction shows that the measurement of a object with respect to the rest frame and with respect to the moving frame. It is also known as Lorentz contraction or Lorentz Fitzgerald contraction. Land contraction was postulated by Georg Fitzgerald in 1889 and Hendrik Anton Lorentz 1892 to explain the negative outcome of the Michelson-Morley experiment and to rescue the hypothesis of the stationary ether. Michelson-Morley experiment shows that ether not exists. So, land contraction is the one of the main reason behind this in Michelson-Morley experiment. So, it is already explained in our previous classes. Although both Fitzgerald and Lorentz alluded to the fact that electrostatic fields in motion were deformed, it was considered an ad hoc hypothesis because at this time there was no sufficient reason to assume that intermolecular forces behave the same way as electromagnetic ones. In 1897, Joseph Larmor developed a model in which all forces are considered to be of electromagnetic origin and land contraction appeared to be a direct consequence of this model. So, in this regard Larmor developed a model that is known as Larmor model in connection with land contraction. Yet, it was shown by Henry Poincare in 1905 that electromagnetic forces alone cannot explain the electron's stability. So, he had to introduce another ad hoc hypothesis, non-electric binding forces ensure that the electron's stability give a dynamical explanation for land contraction and thus hide the motion of the stationary ether. Eventually, Albert Einstein in 1905 was the first to completely remove the ad hoc character from the contraction hypothesis by demonstrating that this contraction did not require motion through a supposed ether, but could be explained using special relativity which changed the notion of space, time and simultaneity. Einstein's view was further elaborated by Hermann Minkowski, who demonstrated the geometrical interpretation of all relativistic effect by introducing his concept of four-dimensional space-time. In Minkowski diagram shows that how space and time working together and the Lorentz transformation equation we get the equations are x dash is equal to x minus Vt divided by root over 1 minus v square by c square, y dash is equal to y, z dash equal z and t dash equal t minus vx by c square divided by root over 1 minus v square by c square. So, Minkowski diagram apply here in case of the land contraction. First, it is necessary to carefully consider the methods for measuring the lengths of resting and moving object. Here, object simply means a distance with endpoints that are always mutually at rest, that is, that are at rest in the same inertial frame of reference. If the relative velocity between an observer and the observed object is 0, then the proper length 0. So, of the object can simply be determined by directly superposing a measuring rod. So, we get always initial point and the final point, and then we measure the length of the object, and we observe from rest frame and the S dash frame, moving frame with a constant velocity. Another explanation definition: if there are two observers who are in relative motion and they try to measure the distance between two common points, then they will end up measuring two different distances. In fact, a person who was moving with respect to reference frame will measure a distance which is shorter compared to another person who is measuring those distances in a rest frame of reference. So, there are two observer, one is a rest frame and another is moving with a constant velocity, and they try to measure the length of a rod which is at rest frame, which from rest frame and the moving frame with a constant velocity. Moving objects are shorter compared to the same object in a rest frame of reference. So, this kind of contraction in the length along the direction of motion is known as length contraction. So, it is definition of length contraction. Now, in this connection we get a experiment, thought experiment. Let us imagine there is a train which is moving in a certain velocity in a given direction, and there is a certain setup inside the particular train. So, in this slide we consider a example which is a moving train, and inside the train a entire setup is given, so that we can do this experiment nicely. So, here given, let us suppose there is a bulb on one end and of the train and there is a mirror on the other end of the train. So, two situation here, one is the bulb given in the on one end of the train, and other side opposite direction one mirror given. So, that light and bulb and mirror they working face to face. So, in this way they are set up inside the train. What happens is that the bulb emits a short pulse of radiation of light photon, and the light photons can travel along the length of the train, reach the mirror, get reflected backward and travels back and reach the initial point. So, bulb emits the light photon, and then light travel along the direction of the train, and then reach the mirror, and again reflected and backward direction the light travels, and again light reaches the initial point. Now, if I want to calculate total amount of time period of light from initial to mirror and mirror to initial point, it can be calculated in a simple manner. So, now we are going to calculate the time from initial point to mirror and mirror to the initial point. So, for the inside observer we get, after getting the calculation, so this is the picture you can see, the for inside observer we get the delta T1 is equal to twice of delta x naught divided by c, and for second observer in moving direction we get the delta T1 is equal to delta x plus v into delta T1 divided by c, and in reverse direction it is delta 2 is equal to delta x minus v delta T2 divided by c. So, for the time from the initial point to mirror, then we get the delta T1, and then mirror to initial point in case of moving direction, then we get delta x minus v delta T2 divided by c. Now, we get the delta T1, we have one calculation, delta T1 is equal to delta x plus v delta T1 divided by c. This implies delta T1 minus v delta T1 c divided by c is equal to delta x by c. Now, delta T1 common, then we get 1 minus v by c is equal to right hand side delta x divided by c. Again, after simplification we get delta T1 is equal to delta x by c minus v, given it is equation number 1. Again delta T2 is equal to delta x divided by c plus v. Delta 2 is the time covered by the distance by light from mirror to the initial point. Now, we get the total time delta t is equal to delta T1 plus delta T2 in case of the moving frame of reference. So, after calculation we get delta t is equal to delta x divided by c minus v plus delta x divided by c plus v is equal to twice a x c divided by c square minus v square. Therefore, the moving object is shorter than the rest object. So, it was the thought experiment in case of the land contraction. Now, we are going to discuss about some brief history of Lorentz contraction. The observer installs a row of clocks that either are synchronized by exchanging light signals according to the Poincare-Einstein synchronization or by slow clock transport. That is, one clock is transported along the row of clocks in the limit of vanishing transport velocity. Now, when the synchronization process is finished, the object is moved along the clock row and every clock stores the exact time when the left or the right end of the object passes by. After that, the observer only has to look at the position of a clock A that stored the time when the left end of the object was passing by and a clock B at which the right end of the object was passing by at the same time. It is clear that distance AB is equal to the length the earlier distance of the moving object. Using this method, the definition of simultaneity is crucial for measuring the length of moving object. Another method is to use a clock indicating its proper time 0 which is travelling. Now, it is another question how we measure the proper time. So, here question mark given which is travelling from one endpoint to the rod to the other in time. So, how we calculate this? We can explain by the diagram. As measured by clocks in the rod's race frame, the length of the rod can be computed by multiplying its travel time by its velocity. In Newtonian mechanics, simultaneity and time duration are absolute and therefore, both methods lead to the equality of event. So, yet in relativity theory, the constancy of light velocity in all inertial frames in connection with relativity of simultaneity and time dilation destroys this equality. In the first method, an observer in one frame claims to have measured the object's endpoints simultaneously, but the observers in all other inertial frames will argue that the object endpoints were not measured simultaneously. So, we know that what is the inertial frame of reference. Inertial frame of reference means that which frame of reference velocity 0 or velocity constant, that frame of reference is known as inertial frame of reference. So, in case of a clock or any other object, any other particle, so two frame always consider, one is race frame, another is moving frame with a constant velocity. So, in this case here in case of a clock then we also consider the time measured by both frame, S frame and S dash frame. The deviation between the measurements in all inertial frame is given by the formulas for Lorentz transformation and time dilation. It turns out the proper length remains unchanged and always denotes the greatest length of an object, and the length of the same object measured in another inertial reference frame is shorter than the proper length. This contraction only occurs along the line of motion. It is a brief history of the length contraction, and again we want to say that any observer co-moving with the observed object cannot measure the object contraction because he can judge himself and the object as at rest in the same inertial frame in accordance with the principle of relativity as it was demonstrated by the Troughton Rankine experiment. So, principle of relativity principle of relativity states that all physics law must be same in all inertial frame. So, it is proved by taking two frame S and S dash, and then when we experiment a physical law, then we say that it is invariant for the both frame of reference. So, in case of Newton's second law, F is equal to ma. So, we prove applying Galilean transformation equation that F is equal to ma is invariant for the both frame, F is for race frame and the moving frame with a constant velocity. But only in a frame in which the observed object is in motion. In addition, even in such a non-co-moving frame, direct experimental confirmation of length contraction are hard to achieve, because at the current state of technology, object of considerable extension cannot be accelerated to relativistic speeds, and the only object travelling with the speed required are atomic particles, yet whose spatial dimensions are too small to allow a direct measurement of contraction. Reality of land contraction. In 1911, Vladimir Barikak asserted that one sees the land contraction in an objective way according to Lorentz, while it is only an apparent subjective phenomenon caused by the manner of our clock regulation and land measurement according to Einstein. The author unjustifiably stated a difference of Lorentz's view and that of mine concerning the physical facts. The question as to whether land contraction really exists or not is misleading. So, land contraction means that moving object land shorter than the rest object land. So, is it possible or not? So, it is a question that is both observer opinion correct or incorrect. So, in this situation it is known as the prediction. So, what is the main what is the correct option, which observers say that correct answer? It does not really exist in so far as it does not exist for a co-moving observer, though it really exists, that is in such a way that it could be demonstrated in principle by physical means by a non-co-moving observer. Einstein also argued in that paper that land contraction is not simply the product of arbitrary definitions concerning the way clock regulations and land measurements are performed. He presented the following thought experiment: let A dash B dash and A double dash B double dash be the endpoints of two rods of the same proper length L naught, as measured on x dash and x double dash respectively. So, he considered a rod and then length are given A dash B dash and A double dash B double dash, and length is proper length given L naught as measured on x dash and x double dash respectively. Let them move in opposite direction along the x star axis considered at rest at the same speed with respect to it. Endpoints A dash A double dash then meet at points A star and B dash B double dash meet at the point B star. Einstein pointed out that length A star B star is shorter than A dash B dash or A double dash B double dash, which can also be demonstrated by bringing one of the rods to rest with respect to that axis. In fact, a person who is moving with respect to some reference stream will measure a distance which is shorter compared to another person who is measuring those distances in a race frame of reference. Moving objects are shorter compared to the same object in a race frame of reference. So, Einstein also said that same thing happened in case of this experiment, in case of rod experiment, that shorter object length is moving object length is shorter compared to the rest object. Visual effects. Land contraction refers to measurements of position made at simultaneous time according to a coordinate system. This could suggest that if one could take a picture of a fast moving object, that the image would show the object contracted in the direction of motion. So, it is another interpretation regarding land contraction. However, such visual effects are completely different measurements such as a photograph is taken from a distance, while length contraction can only directly be measured at the exact location of the object endpoints. It was shown by several authors such as Roger Penrose and James Terrell that moving objects generally do not appear length contracted on a photograph. This result was popularized by Victor Weisskopf in a physics. So, this is one of the important point, that using photographic system we also visualize the length contraction in relativity. Now, mathematical proof of Lorentz contraction. Suppose there is a rod A of length L between x1 and x2 in S frame. So, as we know that we consider always S frame and S dash frame, and if we consider a rod in S frame, that this rod end point x1 and x2 and rod length is given as L. Let us find L dash as measured by the scientist in S dash. So, L is length of the rod with respect to S frame, and L dash is the length of the rod with respect to the S dash frame. And there are two scientists, one scientist in S frame, another scientist in S dash frame. So, now we are going to prove that L dash is shorter than the L. L is the previous length and L dash is the length which is measured from S dash frame. From the following equation, x dash is equal to x minus phi t divided by root over 1 minus p square by c square, y dash equal y, z dash equal z, and t dash is equal to t minus phi x by c square divided by root over 1 minus p square by c square. This equation is known as equation 1. X is equal to x dash plus phi t dash divided by root over 1 minus phi square by c square, y is equal to y dash, z is equal to z dash, and t is equal to t dash plus phi x dash by c square whole divided by root over 1 minus phi square by c square. It is equation number 2. Now, equation 1 and 2 are known as Lorentz transformation, and now we are going to apply this equation for finding the length with respect to the S dash frame. We know that L is equal to x2 minus x1. Now, all of we know that x2 means here x coordinate is given by Lorentz transformation is x is equal to x dash plus phi t dash divided by root over 1 minus phi square by c square, y is equal to y dash, z is equal to z dash, and t is equal to t dash plus phi x dash by c square whole divided by root over 1 minus phi square by c square. So, here we put, instead of x we put x2, and then we put x1, then we take the subtraction which is L is equal to x2 minus x1. After simplification we get x2 dash minus x1 dash plus t2 dash minus t1 dash whole into v whole divided by root over 1 minus p square by c square. Now, see that 1 by root over 1 minus p square by c square, it is Lorentz factor, its ratio is known as Lorentz factor, is equal to, we get x2 dash minus x1 dash whole divided by root over 1 minus p square by c square. Now, here one important point is that t2 dash minus t1 dash equal 0. Now, try to understand how it is it equal to 0, because the both observer see the event at same time, exactly at same time. So, it will be time also same. Therefore, t1 is equal to t2, which are the time with respect to S frame, and t1 dash and t2 dash time with respect to S dash frame, where we have assumed that both the ends of the rod have been measured simultaneously at T1 dash is equal to T2 dash by the scientist in S dash. Writing x2 minus x1 dash is equal to L dash in equation number 3 we get. Now, left hand side it is L. So, in right hand side x2 dash minus x1 dash, it is the x2 dash and x1 dash is the end point of the rod and which is measured from the S dash frame. So, if we write x2 dash minus x1 dash is equal to L dash, then we get that L is equal to L dash divided by root over 1 minus v square by c square. So, this implies L dash is equal to L into root over 1 minus v square by c square. Now, this is the important terms, that is 1 root over 1 minus v square by c square always less than 1. So, why it is less than 1? So, now try to understand that v is equal to what and c is equal to c meaning and v meaning. So, v is the velocity of the moving frame and c is the velocity of light, and this ratio, this root over this term root over 1 minus v square by c square always less than 1, because any moving particle always less than in comparison with the light velocity, speed of light. So, v always less than c. Therefore, this term root over 1 minus v square by c square less than 1. So, we get by equation 4 L dash less than L. So, we get the length measured from moving frame is shorter than the length measured in rest frame. If there is in S a rectangular body of volume V is equal to LBH, L being the length along the x axis, B the breadth along the y axis and H the height along the z axis, then its volume measured from moving frame would be V dash is equal to L into root over 1 minus v square by c square into B into H. After calculation, we get V into root over 1 minus v square by c square, because LBH is the volume given. So, in this case we consider a rectangular body, and this body volume we assume, we suppose that small capital V with respect to S frame and capital V dash with respect to S dash frame. Then we get a relation between V and V dash, volume relation between rest frame with respect to rest frame and with respect to the moving frame. So, we get by equation number 5 V dash is equal to V into root over 1 minus v square by c square. So, here also we get same condition here, root over 1 minus v square by c square less than 1. Therefore, we get V dash less than V. So, volume of a moving object is less than the volume of a rest object. Another explanation, in my previous lecture it is discussed about relativity of simultaneity. Another counterintuitive consequences of relativity that confuses the heck out of people. This is the idea that different people see length differently. So, in length contraction we see that different observer get the difference length of the same object. It is known as length contraction. How it is possible? We just start out with the standard Lorentz transformation equation, and remember what these two equations mean. We have to observer looking at a situation, for one of them the situation is not moving, for the other one the situation is moving. Typically, we say the person seeing the situation not moving in the unprime observer and the moving person is the prime observer. So, in this situation, all we want to do is measure how long a stick is. So, first you remember that Lorentz transformation equation. So, we only get that changes in Lorentz transformation equation in x direction and in time component. Other two axes are parallel, y and z axes are parallel. We get only changes in x direction. So, x dash is equal to x minus v t divided by root over 1 minus v square c square, and time component also says it is t dash is equal to t minus v x by c square whole divided by root over 1 minus v square by c square. And we see the two situation here, one moving observer, another is rest observer. Now, in case of a stick, this length contraction also explained. So, this is the picture 1. See, one is the moving observer and one is rest observer. Rest observer is the unprime observer and moving observer is prime observer. Prime observer say that unprime observer is moving with respect to the prime observer, and unprime observer says that prime observer is rest and is moving with respect to unprime observer. So it is the main condition in relativity. See, in case of stick in picture 2, here we want to measure the length of this point 0 and 1, 1 and 2. Similarly, we can take the length 0 to -1 and -1 to -2. In case of a rod, initial point it is x1 dash t1 dash, it is 0 0, and x2 dash t2 dash. After observation we get gamma L and gamma v by c square L, and after subtraction we get x2 dash minus x1 dash is equal to gamma L. And I measure how long it is. The way actually do this is to find the location of one end of the stick and then the other end of the stick, and then subtract these two location. So first we need to find the initial point, then we find the final point, then we after subtraction we get the exact length of the rod. Suppose you had a meter stick and you label the ends A and B. You could put end A at location 1 and put the other at location 2, which we will call x1 and x2. x1 could be at position 0, then x2 could be at 1 meter. Subtract the 2 and you find that the meter stick is indeed 1 meter long. Now you could have picked other location. X1 could have been 98.3 meters, which means that x2 could be at 99.3 meters, and if you subtract those again you get 1 meter. So each distance of 2 point is 1 meter. So any 2 points we can choose in this stick, then we get the distance between 2 points is 1 meter. Let's make it more interesting and not use a meter stick, but rather some stick with an unknown length that will call capital L. Let's say that the unprime observer, suppose rather that other end of the stick at location x2 t2 is equal to L0, and x2 minus x1 after subtraction initial final point minus initial point, it will be L. Then rather obviously the other end of the meter stick is at location equals L. Putting this in terms of x and t's, we could say x1 and t1 equals 0 0 and x2 t2 equals L0. So let's put those points into Lorentz transformation equation and see what the prime observer says. For location 1 you get the same 0 0, but for location 2 you get x2 equals gamma L and t2 equals gamma v over c square times L. x1 dash t1 dash 0 0 and x2 dash t2 dash, it is gamma L and gamma v by c square L. Pushing ahead, you could then subtract the 2x according to the prime observer, and you would get that the length according to the prime observer would be L prime equals gamma L. Since gamma is greater than 1, that would mean that the moving observer would see a longer length than the stationary one. So in case of meter stick also it is proved that length contraction happen. As we know that the speed of light is constant, which is second postulate of special theory of relativity. What does it mean? It means that if I am at rest and I am measuring the speed of light in vacuum, I will measure it to be c. If there is another person traveling in a very high high velocity in comparison to me, and he measured speed of light is also c. To inertial observer, myself and somebody moving in high velocity, both of us measure speed of light to be the same. In special theory of relativity there are two postulates. One is principle of relativity and other is second postulate is the speed of light is constant for all observer. This simple fact about the nature of our universe has certain consequences. The fact that two different inertial observers measured the speed of light, the same also ends up creating a scenario in which measurement of distances and measurement of time period are not absolute anymore. it means that two observer in relative motion may see that distance between two points. So, due to this principle of relativity, that speed of light is constant for all. So, this created the scenario for these consequences, which are known as Lorentz consequences. Now, we are discussing length contraction, that means contraction in length we discuss. So, in case of rod we discuss, in case of a clock we discuss, and so many objects we can consider in case of the length contraction.